So if you have worked with hyperspectral or thermal images, you have probably seen images like these that are corrupted by stripe noise. One of the approaches to solve this problem is to take the Fourier transform and remove the corresponding pixel in the frequency domain. So the idea is essentially each pixel in the frequency domain represents a frequency in the spatial domain. And because of the frequency nature of the stripping noise, it appears in the frequency domain in an object-like form which we can mask out. And to automate this process, since units are really good at masking, that was a choice we went with, but using neural networks on satellite imagery and frequency domain raises some challenges that in this work we are trying to resolve them. My name is Moien Rangzan and I'm a master's student of remote sensing at the University of Tehran, Iran, and I'm presenting to you removing a stripe noise from satellite images using convolutional neural networks in frequency domain supervised by Dr. Sara Attarchi. So as you know, satellite images are massive in size, and training a neural network on them takes a lot of processing power. To heavily reduce the processing cost with the minimum loss in precision, we use the fact that when you downsample an image and take the Fourier transform, it is virtually the same as cutting the center of the Fourier transform of the original image. So if we have an image with a stripping noise and the corresponding noise pixel is on the 7 pixel from the center, or the DC component, if we downsample the image and take the Fourier transform, that noise would still be on the 7 pixel from the center. And this is because the stripping noise in satellite imagery is mostly low frequency, and when we downsample the image, we can still see the noise in that downsampled image, thus we can still remove it. So what this gives us is we can downsample an image, take the Fourier transform, mask out the anomalies, use zero padding to make the mask the same size as original image, apply it on the original image, and still get rid of the noise. The other challenge was the uncertainty of what satellites can capture in their images. There are many artifacts on Earth's surface that can create noise-like anomalies in the Fourier transform, like agricultural fields, shorelines, and cloud shadows. And it is hard for a normal unit to distinguish these artifacts with the noise since we are throwing away the phase and we are just giving it the magnitude of the Fourier transform. To resolve this problem, we came up with the idea to not only give the Fourier transform to the unit, but also give it the original image so it can learn what are the noises, what are the features that look like noise, and have a better result. For our dataset, we downloaded a satellite imagery dataset from Kaggle, which is from the African country Malawi. We added synthetic noise and we took the Fourier transform, and for the noise mask, we detected the change in the Fourier transform before and after adding the synthetic noise. Our dataset consists more than 6,000 images. For our neural network, we give it an image with 2 channels, which we stack the original image on top of the Fourier transform. And in the middle, we added the dense layer to amalgam this data and somehow create some connections. And I got the idea from the YOLO original paper. And this is how it works. In the contracting part of our network, we use cross-conv2D layers, and these kernels have different weights for each layer. So some of them can be specialized in learning about the spatial features like the orientation of the noise and the features in the image, and some of them can be specialized in learning about frequency features like noise hotspots in the frequency domain. This data goes down into our dense layer, and now it can think, okay, this is the orientation, these are the hotspots, these are noise, and these are not. And it sends the data through our up convolutions and in the expanding layer, which creates the final mask. The final training results show low bias and low variance, which means we have low overfitting, and it was expected since we use synthetic data with a normal distribution. As you can see in the final results, features that created noise-like anomalies in the Fourier transform, some of them were able to trick the normal unit to think that they are noise, but our proposed network never made a mistake throughout the whole test images. These are some of the final results. And we also applied this algorithm on a Landsat scene band 3 on Brazil, which had a memory effect which caused it to have some stripping noise. And it actually worked. You can see we applied it on the image, downsampled image. And we also applied it on the original size image. And this is the final image before filtering. And this is the one after. And you can find the whole project on my Kaggle account. Thank you all for watching. It was an honor to be here. I hope to see you guys next year. Have a blessed year and peace.